like to say thank you very much for inviting me here. This Summit on Life Science and Regenerative Medicine is hosted by the AZD Foundation and BioLink Biotechnology, and I give special thanks to them for inviting me and to the President, Mr. Yu, for inviting me. But healthcare is going through a revolution inspired by AI being applied to health. We have a situation now where you can have wearables, you can have other monitoring systems, and you can have diagnosis and so forth done by AI systems, and that will provide you better healthcare than going twice a year to the doctor. We're at the point where that's technically feasible and very straightforward, and will be more so in the future. It's the idea that you want to have health and you want to have anti-aging, you want to have longevity, a good, healthy life. That's the goal. This allows you to do that and allows you to make dental care more personal because you're applying AI. The cellular genetic treatments, which is what we're here for, is particularly important via the stem cells, but there are many ways now of people learning. The Nobel Prize this year in physiology was for a way of making more adult cells back to being pluripotent, not perfectly good because there's some errors and stuff, but we have to have a deeper understanding of cell function and growth signals. So one of the things is, just because you do cell therapy doesn't mean it's going to work. You also have to put out the growth signals which cells communicate to other cells that it's time for them to do so. So classic is weightlifting. You have to do a little damage to some of your muscle cells so they send out the growth factor signal and more muscle cells are done. That's something I learned many years ago, but now it's true in many areas. Another big tool that we have is the CRISPR-Cas9 gene editing. That has really revolutionized the way we're doing things now. But the thing that you should note is at the current time, there are more than 5,000 gene cell therapies under clinical trial. 5,000 now. That means we don't have that many diseases. That means they're redundant. Some of them are redundant. There are different ways of approaching them. Robotic surgeons and robotic doctors. So I have a picture here that I'm standing in front of. This is Qi, I think it means little doctor in Chinese, if my Chinese is correct. It was first put out by a group from Tsinghua University and related companies, and it passed the medical exams 5.5 years ago and did better than 80% of all the doctors. These doctors should be in most hospitals and certainly in small towns already. They're much cheaper to make as doctors, and they're better than most people as doctors. And you can put them in villages and they don't care. Right? Whereas a lot of the other doctors don't live in big cities. But robotic surgeons and diagnostic and prescribing chatbots, basically, are better than humans. And combined with a very outstanding human, 5 or 10 of them can do the work of 10 average ones and be much better. This is the slide that I've shown for many years. The thing that I have gone around and give talks about is that when babies are born, you should save the umbilical cord stem cells and freeze them for future use after you take a certain section of them and do careful DNA analysis. So you have that data, and that data tag goes with the human for the rest of their life. Those stem cells are there and they're preserved. We have to make stem cells other ways, right? And they're not as good as having the very young stem cell. This was the chart that I pulled up. The type of diseases that were treated in 1988, sorry. In year 2000, 10 years later, 2017, instead of 40 types of diseases, 80 types of diseases. What is it going to be in 2 years, next 10 years? It's going to be more than 200. It's clear. We know that. We know there are trials going on. We know that some of them succeed and they're going to do that. Here's another piece that gives you data. This is from 2012, but this is the number of clinical trials that are being done at some point in time. Now it's over 5,000. The growth and possible treatments by stem cells is just a steady increase. It's almost a certain percent per year, not quite. It's not quite keeping up with that. Clinical trials are not cheap, but people are realizing that they got to do them because I see things show up that I didn't know before, that the mesenchymal stem cells, they don't really start until 2004. Now there are already treatments. Now, why is that happening? It's happening because we finally have the science and the capability of doing it. And if you pay attention, UCLA's are getting faster and faster. They're doing the DNA scans are improving, doing the telomere scans. All that technology is improving all the time. You can do all those things much better. Those are engineering and physical kinds of discoveries and technology being pulled into this field. And we're going to change it very much. Here's the stem cell market forecast. Okay? We're in 2024. We think it's almost 19 billion a year. By 2033, it will be around 55 billion per year. It doesn't look too impressive, but that's more than 12% per year. That means it's doubling on the time scale of roughly 5 years. What it means is there's a lot of competition. I didn't put a plot how many places are doing stem cell stuff, but it's a very active kind of field. So the fact is the demand is going to be there. Certain companies are going to take that demand. So that's the issue about what do you do to keep being one of the high-quality, low-cost producers, to make products that people use and are reliable and are cheap. And already we're seeing the stem cell therapy have a set of low-cost providers. Costs in the United States for stem cell treatment, $20,000 to $50,000. Whereas if you go down to Mexico, it's $3,000 to $1,500. But here, we're talking about Thailand, it's down in the 3,000 to 13,000 range, typically for what's going on. And its main competitor right now is Turkey. That's why I have this chart on the right. These are from Thailand, from Turkey. Here are the kind of treatments that are advertised. And I think Thailand could have the wisdom to make sure they keep the quality of the product high, even though they're driving the cost down. And here's the geographic location of where the primary clinical trials are going on. And you can see a big fraction of the United States, detailed in the United States down below, Europe, and somewhat in China and Southeast Asia, but not as much, although it's growing up. When I look at the latest chart, not more clinical trials starting in China than there used to be. But that doesn't matter. It doesn't matter where the clinical trials have done, the discovery of clinical trials done. It matters who makes the quality treatment. This is not about clinical trials. This is about how do I make a product that goes to the customer and provides them the help. So this is the old slide, but I put it in here just to show you. This is a company in Hong Kong. You can make a contract with this company. They will come and take the sample from umbilical cord, and they will take it and freeze it, put it in a car, take it to their lab, and store it. That's something I think all countries should be thinking about, just having that be automatic, that the hospital has an automatic system to take the stem cells and the information to a laboratory which does the DNA analysis and does the preservation. So here's another example for stem cell regenerative medicine and spinal cord injuries. You want to be able to solve that problem? Well, it turns out that you can do it by having alignment of surgery, but there's a stem cell treatment for that, where you get a sample of from the bones and you make the kind of cells and go back and try and regrow the whole area. And so this is just an artistic drawing of this person has a lower back spine problem, right? Here's the lab, and it's clearly done by humans, right? I'm going to show you what a lab that's done automatically should look like. A large fraction of people have problems with their spines, their backs. Right? So this is going to be one of the treatments that's going to be a big seller. So now you get down and make the cell therapy workflow line. If you're going to automate, you have to know what's going to happen at every step. There's the part there, this is the lymphopoiesis, that's when you're taking the T cells, and you take it in the blood and you separate the T cells out and you process them. So that's all done. You got them in storage. Now you need them, you thaw them, you select some of the good cells. One of the things we're going to do is improve the cryopreservation so that when you thaw them, most of the cells are good. And then you can do the treatment, you can do the activation and gene transfer, Cas9, you do the cell expansion, right? You do a bunch of testing to make sure it's all good and everything's good, and you freeze most of it, and you only take part of it to treat the patient because you know you're probably going to need some more later. And that's the whole thing. I think the part from the storage all the way here before you do the fusion. That should become all 100% automated. I have this slide just as a reminder that in fact, the cell preservation is only half the job. It's doing the DNA analysis, it's keeping the records of the patient where the cells were taken, keeping track of that, making sure that nothing's done to spoil them and so forth. So there's a huge amount of software and data storage that goes along, and that data is worth about as much as the cells. And you have the same sort of issue for storing cells as you do for storing data. You want to have two geographically independent locations, and you want to make a highly reliable system so that a typhoon coming through Shanghai doesn't kill your power for a week and run over your cells. So this is just here to say half the job is software. It's AI software, but it's software, and it's tracking everything. It's the same thing, the same basic thing. You got to get the blood sample out and separate out the white cells. Here, it's magnetic monoparticles. They're run through the cancer. This is a thing that I thought about many years ago. The antibody-coated beads go through the tumor. They get pieces of the tumor cells. You bring them in and you activate the cells that way. You do through the whole thing. You do the expansion, you do the bleed removal, and you put it back in the patient. Okay? Those are two different paths, and you can do two different levels of automation. You see, the first part is collecting it and separating it and cryopreserving it, and then there's a separate wing, which is in blue, which is what you do to remove it. So you can think about a situation where the patient has a sample taken, the blood is flown in a special container from whatever city they're in to the factory where you're going to make the treatment. But it probably makes sense to have very close to the factory where you actually give the treatment. They stay in a hotel and they check to make sure they're okay. They're in the hospital when they get in treatment. They're in a hotel making sure they're recovered okay, and then they go fly home back to their country. You have to figure out what the best strategy is. How are we going to automate this? How do we start doing this? And the answer is, once you have the workflow and once you have the details, there are people making certain steps, but you don't need the people to make a lot of the steps. There are robotic arms and other things can do a lot of the things. And even the AI systems can look at the cells through microscopes. And that can be all done in a sterile atmosphere. So here's the example. These containers are cryopreservation containers. They're digitized to the extent that you know what samples are in there, what conditions are in the sample. You can say, I want the cells from such and such, or I want the samples from such and such a person, and it will do that. And here it's showing people without hairnets on and all this kind of stuff. My vision is this is in a room that's full of dry nitrogen or through sterile air situation, and there are sterile feed-through windows that let you go, either bring the samples in or put it out, but everything is done by automated systems. Essentially, the robots go to each one, put the stuff in, label it, and you're tracking it, and you're tracking conditions inside of each one. And you have a bunch of them. How are you going to scale this with time? As you get more customers, you've got to have more samples and more time. You get able to grow carefully over time and have the automated system work. Here, you buy from various companies and you put it together and you make an automatic feed from one to the next. This is an example of a real automated arm coming out and activate the cell. You can buy all the pieces, or you can buy from a company all the pieces strung together so that you can do basically automated. Now, it's not completely automated, it's close to automated, but eventually you want it to be completely automated. So here's another example. Here's a cryopreservation tank, and then there's a larger sample. Here you've already expanded the cells, and you want to keep a larger sample. And you pull out the sample that you wanted to have with a robot arm, and hand it to a system that carries it out to be revived, basically. This is a higher one, it's also a liquid nitrogen one. It's stainless steel ones, and it comes in a couple different sizes. The ones that I've seen in real life a number of times are quite large. They're 1.5 meters or 2 meters across, and they hold thousands of samples. And you don't let a human touch them. You have it all automated like a jukebox. So this is a drawing I made, but it wasn't me that made it. I have sketches I made by hand. This is, I was sitting in my office in HPUST, and I was envisioning how an automated system has to be and how it would grow. And I said, all right, I want solar cells and liquid air making, so I have liquid nitrogen automatically with the solar cells to back up in case typhoon comes and powers out or whatever. And gravity feed, and down inside, stored inside the mountain, I have reserved things. They're protected against all kinds of things, including cosmic ray electrons. You want to be 20 radiations deep. You're going to keep these, if they're stem cells, umbilical cord stem cells, you're going to keep them 40 or 60 years. Is the kind of thing you have to think about what secondary effects could kind of be. And basically, cosmic ray muons come through about 1 per hand per second. But every now and then it's like a shower. They don't go very deep. You just need a particular layer. And then you can have export windows so you can bring stuff in or export the stuff out to these automated stations to produce the product you want and then send some of the stuff back in for permanent storage. But that's thinking it much further. So I gave it this description and it gave me this thing. I had imagined the solar cells on top, the big liquid hydrogen tank, gravity feed, now I think 2, in the next sketch, last sketch I think it's 2 of them. And you feed those down, so the power goes out or anything happens, you're automatically still able to keep things cool for a few days. Then you have the cryopreservation area, and then you have in a separate room, and then you have the feed-throughs out to where you're either bringing them in or out to where you're creating the solution. And so I wasn't that happy. It made a pretty picture, but I wasn't very happy with this picture, but it gives you the idea of the scale of thing, just to be starting out, but you've got to allow for expansion. It showed the right scale that you might have to come to eventually. The AI wants to make pretty pictures. The AI is not very advanced now, but just wait 5 years, the AI is going to be way more advanced. But you have a lot of tanks where you're storing stuff. You know, if you're going to be storing stem cells for everyone in, say, Beijing, that's a lot of stem cells. It's going to come to millions. You've got to figure out how can you store those in an efficient way and track them and keep the data for all the years that you need to be doing that. But this is just to give you an idea how you think. And then I tried again, why isn't it closed? And why are there plants in there? But the fact is, this shows a really bright scale of what you may be looking at 10, 15 years from now, right? You want it all automated, you want it all system. When you build your stem cell factory, or whatever you want to call it, storage place, you got to have room for a lot of expansion, because you're going to build the business up quite a lot. And that's why, if you're doing it here, you want to have it in a place where you can expand, and you don't want to put it in the floodplain for a river. You want to put it in a place where, if there's a huge typhoon comes through here, it will survive readily and keep your things together. This gives you the kind of scale you've got to be thinking towards. Not now. You build simple stuff now, but you've got to be thinking, how am I going to expand to be able to hold 1 million samples? That's the kind of scale you have to be looking for. In a country like Thailand, you could choose to take and make stem cells, build cord stem cells for the population. 20 years from now, 40 years from now, they're going to really appreciate it, but they got to protect it till then. But if you're just going to run a big business here, you're still going to be doing 1 million kind of numbers. Here are my conclusions. The end of this talk is just the beginning of where we want to be going in the future. We want to be thinking how to automate, how are we going to expand things in the future to be able to have like an almost continuous process of taking the patient's cells, taking them in storage, taking them out of storage, activating them, and going on. And it has to be done as a batch job because every patient is different. That's why we're doing stem cells. It's a rapidly evolving industry. So, according to Confucius, failing to plan and when there's rapid change is a plan to fail. Right? So you really have to think, where am I going to be in 5 years? Where am I going to be in 10 years? Where do I want to be when AI is doing everything, which is 20 years from now? Essentially, AI will run these factories. We want to be really automated for the cell procurement even, and especially processing the cryopreservation. And this is a route to a reliable process and low cost. Thailand has to keep the quality up, and it has to automate, and then that's the only way to keep up with the field, because there are going to be fewer companies and places that are doing this. Quality, reliability, and safety are paramount to what's going on, now an automated system can make it work that way. This is really interesting to me and challenging to me. I really look forward to this evolution and things that are going on. Thank you very much.
Thank you so much.